Hey everyone, and welcome to the channel where today we are going to be talking about a new method, a new paper that came out within the last 2 months that allows researchers and anyone really to train models with trillions and trillions of parameters. It's really crazy. Yes, this is a new paper by Microsoft where they trained a 32 trillion parameter model, and then they also fine-tuned a 1 trillion parameter model with only one cluster of 16 GPUs, which might sound like a lot, but if you're doing something or if you're utilizing cloud computing, that's actually not too much to get your hands on for most researchers. Now, as I was first reading through this paper, I was honestly not gonna lie, dredging through it a little bit. I was like, will this really be an interesting concept? But the more and more I went through it, the more I was really intrigued by what a feat of human engineering this really was. This is really a paper about a system of parallel computing that's just been optimized to its absolute core. Usually I'm more on the side of I like to just read core machine learning stuff, really the theory, but this is a systems problem, really with a sort of machine learning wrapping over it. So I wasn't thinking I would like it as much as I really ended up liking it because it's incredible what they've achieved in this paper. So that's why I'm really excited to share it with you all today. Specifically, I'm going to be talking about first the previous method that we were using to do this sort of parallel computation, and then I'm going to move into talking about this new method. What's different, specifically what are the different components of it and how it works. And then lastly, I want to wrap up by talking a little bit about how you can actually get your hands on this technology as soon as today, because there are actually already a lot of libraries that are using this paper. Now, if any of that is the type of thing you like to watch or listen to, do consider subscribing to the channel. I talk about a whole lot of related content, anything from research to my experiences at companies like Google and Amazon to doing research, all sorts of reinforcement learning stuff, all sorts of stuff. So if you are interested, it does help out the channel a lot and it does mean a lot to me. But anyway, without further ado, let's first jump in to a little discussion on how we've been handling this parallel machine learning data stuff up till now so that I can really set the stage for how we've progressed and what this new paper really brings to the table. Okay, so here we are in the paper. I want to start out by talking about the setup here, why this paper was so necessary, and sort of what the motivation behind this was. If we look at the abstract, we can see they point out that within just the past 3 years, model sizes have grown 1,000-fold. This is to reach hundreds of billions of parameters. They're probably referring to GPT-3 right here, although I think there are other models now that also reach that size, which is crazy, right? That is absolutely ridiculous. GPU memory, on the other hand, has only grown roughly 5 times. 5 times, 1,000 times. Clearly, the scaling doesn't match up here. So we essentially need new ways of accounting for this. Right now, to train a trillion parameter model, it takes 800 NVIDIA V100 GPUs, and each of those GPUs are quite pricey. It's a crazy amount, right? This clearly is not scaling very well, and something needs to be done about that. And that is why we have Zero Infinity, this paper, and great name, by the way, breaking the GPU memory wall for extreme scale deep learning. So that's sort of why this needs to happen. So the method that was being used before, let's go up here real quick, was called 3D parallelism. Hopefully I spelled this parallelism, I think. And essentially what this is it's a method where you essentially break up your model into different pieces, different tensor slices, and you run those computations in parallel across different GPUs, right? So essentially all the parameters just sit on different GPUs and you do different computations on different GPUs. It's fine, right? But once you take into account that 1,000 to 5-fold increased comparison, well, clearly we really are running out of GPU memory, so we need to do something about that. So there's a few problems with 3D parallelism. One is what I just mentioned, right? Not enough GPU space. That's a big one, probably the biggest one. And not only do we not have enough GPU space, but sometimes when you're making these models with 3D parallelism, you have this sort of constraint you have to work in which is the largest single layer in your model has to fit into a single GPU. So if your single largest layer, even though it's just a single layer, is larger than the amount of space a single GPU has, you actually can't run that model. So it doesn't work for all models. That's a huge downside, right? We want to be able to fit essentially whatever model. If we want to do super wide models, we don't want to be limited by that. And then the other sort of downside here is that this just takes time. It takes time. It's sort of a pain. You have to refactor your model to use 3D parallelism, where ideally this whole process should happen automatically. You don't want to waste your time doing all this engineering when really you just want to be working on experimenting with new ideas and seeing what works. So really the goal here is going to be, the biggest goal is to be doing this automatically. So I guess we should say goals, and this is sort of what the paper does, is doing this automatically. And not just automatically, but doing the scaling to not just GPUs, but also looking at CPU memory and other memory. Specifically, what they end up using in the paper is NVMe, which you can think of this as, I'm pretty sure this is just SSD, and the E is supposed to be lowercase if it really matters. But this is basically just SSD. I think NVMe is a way to communicate with SSDs. I think you can double check that, but essentially we want to use non-GPU memory. So that's sort of the goal of this paper, just to give you a little background. So this paper came out just roughly 2 months ago from now. I think it was in April, and it was released by Microsoft. Unsurprisingly, the company that's now working with OpenAI that is building these huge models, right? So that's maybe a little bit of why there. And just taking a look at this paper, initially we can see a graph on our right here, or yeah, I guess this is a graph, a bar graph to be specific. And what this graph shows is really kind of crazy. If you look at this, this is the different scaling between 3D parallelism, which is what we just talked about, and the new method, zero infinity. So they start off with NVIDIA V100 DGX 2 nodes. So each one of these nodes, by the way, I think has 16 different GPUs. So keep that in mind. So we can multiply each of these numbers by 16 to get the number of GPUs. So for 16 GPUs, they can run a 1 trillion parameter model with this new method. In comparison, previously, they couldn't even do, what is this? This was like 20 billion, I think. Yeah, 20 billion. So that's a huge increase from 20 billion to 1 trillion. And these both scale linearly. It might not look like it because of the axes, but these both do scale linearly, which is really great. That means every time you add a new GPU, you're essentially getting an extra 60 billion parameters roughly that you can add to your model. And I know I just said this, but I want to reiterate this just because of how incredible it is. This is 50 times better than what we had before. So if we could train a 1 trillion parameter model before with our hardware, now we can train a 50 trillion parameter model. Huge difference there. So huge improvements, and that's really great. Now, I will say a little caveat. This is linearly scaling, but they don't show from like 1 GPU. The scaling starts with 16 GPUs. So I don't think it actually starts from 1 GPU. It might start from around 8 or something. I'm not exactly sure. They don't go into that. So you won't get this as good as results if you're using a single GPU at home. You probably won't be able to train a 60 billion parameter model. But what I found, I looked around a bit and I found that 13 billion was roughly where it starts with 1 GPU, which is still really crazy. That's still enough to train GPT-2, at least memory-wise, not compute-wise, but memory-wise, you could put GPT-2 on a single GPU with that. So really, really great there. So that's a preview of the results, but now let's talk about how this actually works and what we need to do to get this to work. So if we actually scroll down quite a bit here, they have a, sorry, my mouse is in the wrong place. They have a little graphic right here that is very helpful in understanding how this works. So what our goal is essentially to take all these parameters we have and move them throughout the GPU, the CPU, and our SSD as necessary, right? So let's first think about what we actually need to be storing and transferring. Well, the first thing are the parameters, right? We can see that right here. So the parameters are one thing, but there are actually 2 other things that take up a lot of memory. The first one you might have thought of is the gradients. So the gradients are really important when we're doing backprop. We need to make sure we have a place to store those and are roughly the same size as the parameters. What's the last thing though? There's actually a huge box here you can see I covered up. This probably you don't think about as much, but we actually have optimizer states. So this is if you're using something like an Atom optimizer that actually stores a bunch of variables for all your parameters. And this is very essential for training huge models, which is what this paper is all about. So we can't like throw these out, right? We need these too. So these are the 3 different, we call them model states that we need to be accounting for. So at the very startup of this model, when you start running the training, the first thing that happens is we use the Infinity, or this paper uses what's called the Infinity offload engine, which is something that Microsoft has developed, I believe, to
do that whole thing automatically, right? We take all these and we decide what's going on the GPU, what's going on the CPU, and what's going on the SSD or the NVMe. So right here you can see we go from here, the model, to distributing this on the slow memory and sometimes also on the GPU if we have enough memory on the GPU. And that's, again, the really nice thing here is it automatically does this whole thing. So if you have enough memory on the GPU, it will do that for you. But if you don't, it will figure out where it needs to put the memory to make all of this work out. And this is sort of what we talked about earlier, because the previous method, 3D parallelism, you had to do all of this yourself. Well, it didn't even put these here, right? But everything you did do had to be done manually. Here, it's all done for you. And the software is actually open and available. I'll be talking about that at the end of the video. So it's not like you have to code any of this. Very nice. Now, the next thing that happens is we go to actually train, right? So we're starting to train. It puts all these on the right, all these parameters in the right places. And now we're going to do forward step, whatever it's called, where we pass through all of our input data and go through layer 1, layer 2, layer 3. And what actually happens is most of this memory is not on the GPUs. So you can see here, the GPUs are actually reserved if we don't have enough memory. They're reserved for actual computations. So when we get to layer 0, we will essentially say, okay, let's grab the parameters for layer 0, pull them up into the GPUs, do the computations, and then pass them back down. And that's what you see here, this all gather and reduce scatter. It's where essentially the all gather is gathering all the different parameters because they might not all be on the same devices. So it's gathering all the parameters from that first layer, pulling them up to the GPU. And then once we have calculated the gradients, we can send them back down to be with the corresponding parameters. So that's what's happening in this little graphic here. Now, that is all great and all, so this is pretty cool, but it's nothing groundbreaking, particularly because, right, there's some cost associated with all these operations, especially, you know, talking between the CPU and the GPU is quite costly. It takes time, so you might be thinking, well, won't this be a bottleneck, or maybe will the bandwidth be a bottleneck? There's all these sort of different issues we can have. So this design is cool, but this isn't actually where the innovation comes in. This is sort of the easy part. What's really groundbreaking are 3 optimizations in particular, 2 for speed and 1 that allows very, very large models. So let's start with that last one, the one that allows for very large models. And I'm going to zoom out a little bit here and sort of write these on the right here. So the first thing is the memory centric, and they love this word centric. I swear they use it a trillion times in this paper, memory centric tiling. And essentially what memory centric tiling does is it breaks up singular layers. So sometimes we don't have to do this, but occasionally we will have models that are so big and so wide that their single layers can't fit into GPUs. Remember, this was a drawback with 3D parallelism. At that point, in if we were using the previous model, well, there's just nothing, or the previous method, there's nothing we can do here. But here, what this actually does is it breaks up layers. So it breaks up layers and stores their parameters in different places and then pulls them together separately and performs the calculation separately. This means that no matter how big a layer is, we can still break it up and we don't have to worry about running out of GPU memory. So this is a great way to essentially increase the width of models that we can compute. So that's optimization number 1. Optimization number 2 is bandwidth centric. Again, centric, you'll see this a lot more, partitioning. Now, to be honest, this is there really isn't too much interesting stuff about this one. This is probably the most boring of them all. But all it is it's saying the bandwidth that we use communicating between the CPU and the GPU, we need to make that, you know, we can't have that be constant. We need it to scale every time we get a GPU, because if we don't, well, we're going to run out of bandwidth, right? This is supposed to support many GPUs. And essentially what they point out in the paper is the specific way they do the message passing and the parallel computing here using this all gather method, as opposed to, like, there's other ways you could do this using like a broadcast method. If you don't know what that is, no worries. All that you need to know is this all gather method specifically that they use makes this linearly scaling bandwidth, which is great. That means every single time we add a GPU, so if we have 5 GPUs and we add 5 more, that means we're now getting double the bandwidth, which is great. Now, that doesn't mean this can't still be a bottleneck, right? Bandwidth, even if we are linearly scaling, maybe that isn't good enough. And that is where this next sort of optimization comes in super handy, and that is overlap-centric design. I'm actually going to erase these two, sorry, but this next one is very important, and it's going to take up a bit of space, I think. So let me erase these for the most important one. And this is where I think this really is really interesting. The overlap-centric design. Oh, design, I can't spell right now. There's the centric again. They love that word. I don't know why. So there's 4 different types of operations that need to happen when we're doing this whole thing, right? So 4 operations. The first one is we need to read from CPU, right? So we might need to read the parameters from the CPU. We then need to copy to GPU, right? So we need to talk between the CPU and the GPU. And this, by the way, usually takes a long time. If you've ever trained lots of models, you know you shouldn't be doing this all of the time. So you know, this could certainly be a limiting factor, even if we do have linearly scaling bandwidth. But we're going to talk about how they get over that in 1 second. So the next piece is they've gotten all this data on the GPU. Now they need to gather it to one tensor, right? Because it's split up. A single layer could be split up against, you know, across a bunch of CPUs or a bunch of SSDs. So we need to gather those into one tensor. Then we need to perform the computation. So multiplying the weights by the previous layer's input. Now there is a 5th step, right? We need to calculate the or pass back the gradients or whatever, but we're going to leave that out for now just because that's not as time sensitive. But these 4 things, if we're just doing one after the other, we could very easily run into an issue of not doing this fast enough. So the whole idea is that we want to do all these operations in parallel. And the way it does that is with a prefetcher. Because, and I guess I'll prefetcher, write this out first. This is the key here, this prefetcher. Now, we can't copy something from the CPU to the GPU if we haven't read it off the CPU yet. We can't gather things into a tensor if we don't know what those elements are yet. And we can't perform a computation if we don't have a tensor to do the computation with yet. So how do we do this in parallel? And the answer is that we look many, many steps ahead and start calculating steps ahead before we even get here. So the prefetcher at runtime, which I think is really cool, it does this at runtime. You don't need to define, well, I guess you do sort of have a graph defined, but not in a super complicated way like you used to in TensorFlow or anything. But the prefetcher will look ahead, right? It will look ahead at the layers to come. So say we're on layer 0, it will look at layer 1, and it will say, what are we going to need? Well, we're going to need parameters P1 or whatever parameters there are, and it's going to start these steps already. And if it has more bandwidth, it might even jump ahead to the next layer and start the steps even while we're still doing the calculations for layer 0. So it will start doing all this so that by the time we get to that layer, we already have our tensor and we can start the computation. So that is the way it essentially, it's really, really aggressive parallelism, which is incredibly cool. And this is where the systems design really comes in. If you've ever learned about how computer computations work, how like the clock works, and how you overlap essentially all these different operations, this is probably going to look really familiar to you. And it's really neat that they're sort of bringing this into ML, this super efficient design that we built out for computers, you know, many years ago. And that's why that's one of the reasons I really love this. It's really just been optimized to the core, super, super efficient parallel computing. It's cool, you know, you can't get around it. It's cool stuff. So this is especially really good for a low GPU count. So this is, you know, if you only have 2, 3 GPUs or even 1, this is going to be really great because it's a lot harder to do this when you only have, it's a lot harder to be fast generally when you have 1 GPU and you can't do these parallel computations as much. But if we're doing the prefetching, that is less of an issue, and this ends up helping us out a lot more. So this is really awesome, and the end result is just crazy efficient parallelism. That's sort of an overview of how this whole system works. Pretty neat, right? And you can read through the paper if you want more details. The paper here mostly details sort of the math, how they came to these numbers and stuff. It is interesting, but hopefully this gives you the general idea. So your next question you might be wondering about is, what about the results? What do the results look like? And that is a good thing to question. So let's go ahead and take a look. They have a few graphs down here. Let's zoom back in. Oh no. There we go. So if we zoom down here, we should be able to find a few graphs. Where are they? Where are they? The long paper. Here we are. Here we are. So here they compare the throughput. Now the throughput you can think of essentially as the compute, how much compute we're getting, how fast things are running. That's probably the simplest way to put it. So the higher the throughput, the faster we're training the model. Even if we can fit these giant models onto a small amount of GPUs, we still have to compute fast enough to train them so that it doesn't take us a trillion years, right? That's pretty important. So looking at these, the results are actually pretty good. Now you will see that they don't actually have comparisons with 3D parallelism for lots of this because they didn't have enough resources because it goes so fast. You really can't blame them. It would have cost them millions of dollars probably to run these tests if they needed to do all this. So, yeah. Well, I say millions. I'm just pulling that number a little bit out of my butt. Just looking at GPT-3, though, they might have not had as many epochs and such. Anyway, it would have taken a lot of money and a lot of resources. That's why they don't have the comparison. So just thought I'd mention that. But if we look, so the first thing they have is throughput with the model size on 512 GPUs, keeping that constant. And you can see this does decrease a little bit. Now, it does increase at first from 0.5 trillion parameters to 1 trillion parameters, and that's probably because of this great parallelism that they have going on for them. Now it decreases, I think, did I calculate this? Is like 40% or so. It's roughly 40% going up to 20 trillion parameters, which isn't great. Actually, is this 40? No, this is not 40%. It looks more like 10, 20%. It's not a bunch, right? And I think that's the real takeaway here is it's not perfect, but it's pretty good. It's pretty good, and it doesn't drop that much at all until you get to over 10 trillion parameters. And I mean, we're still working our way towards 10 trillion parameters, so I give this a seal of approval for me at least. The next graph they have right here is the graph on throughput with the number of GPUs. And what is, actually I found this slightly surprising, I guess maybe not because again this goes hand in hand with parallelism, is that the more devices you have to work with, the more efficient you are. But what's really crazy is they have above linear scaling. Now, it's not super above linear, but it is slightly above linear, which means that if you go from 64 to 128 GPUs, and then from you double that again from 128 GPUs to 256 GPUs, well, you don't just get, let's say you get X improvement from 64 to 128, and then you go from 128 to, or I should say 128 to, what's that plus 64? 192. So this is X. Now this, oh, dang it, I keep to 192. There we go. So this is X. Now this isn't just X. This is X plus some constant, right? Essentially all I'm trying to say is that when you add the same amount of GPUs, you're getting better returns each time, which is really great. So this is very impressive. Also gets my seal of approval very much. I don't know what my seal of approval is worth, but it gets it either way. And lastly, we can see on the right here the results without parallelism, which is kind of interesting. I guess they just want to prove that the parallelism is working. And if we do look, we can see a huge downscaling here. So there clearly is some good work going on here. This is, I think, where the 40% decrease was. Yeah, this was a 40% decrease. So the parallelism, as I mentioned, is clearly doing good work here. There's really no doubt about that. Now, they do have a few more results down here if you're really interested. I'm not going to go through these just because I feel like what I've already went through gives you sort of the picture of how great this is. Down here is a little bit more, just more details. So I'm going to link this paper in the description if you do want to go through it, though. I do have a little bit more I want to go over, though, before we end the video, and that is how you can start using this yourself. Now, since this paper has come out, there has been a library called DeepSpeed, and I will actually pull up the page for it right now, the pi, I don't know. Here we go. So this is the page, and as you can see, DeepSpeed is a library that utilizes all these things we just talked about. Now, it actually existed, I believe, before this paper, but it used sort of previous methods, but as this new paper came out, they implemented these new methods within this library. So this is something you can use, and they actually have a tutorial, here I'll bring this up too, as to how to use this. Now, I'm not going to go over in depth this tutorial in this video because I think that's a bit too much, but what I can tell you, because I've looked through it, is that it's really easy. It's surprisingly easy. It supports everything that's on the paper, and all you really need is is a config. Now, I guess maybe there's a little bit more to it, but if you really want to make this simple, what I think goes above and beyond is that this is already implemented in popular libraries like PyTorch Lightning and Hugging Face. I haven't looked at the Lightning implementation, but I have looked at Hugging Face, and I didn't link anything. Maybe I'll link it in the description. But if you do look at the implementation on Hugging Face, they have a little tutorial. All you need to do is nothing more than what you were doing before when you were doing Hugging Face models, right? It's all the same except for you add one parameter that just specifies a config, and the config files aren't too bad. They look something like this, right? It's really not too bad. It talks about just how you want to, bucket sizes, all that random stuff. And they give you some presets here. So it's super easy. It's really great. You can get onto this if you want and make models. I said earlier, I did a little digging, and with a single GPU, it depends on the GPU, but you can model roughly up to 13 billion parameters is what I was finding, which is insane. That's GPT-2 almost tenfold. So you can definitely get GPT-2 running on your own GPU as long as it's not too bad. And yeah, I think this really speaks for itself. It's a great paper. The library is already out, which is super awesome. And I'm really excited to see what people do with this. I think OpenAI has been one of the few companies that's been doing these super huge models. But more recently, I guess Google and Facebook to an extent too. But more recently, we have seen more companies coming out with these huge models. I know Naver is I think a Korean company that came out with a Korean model recently. I think we've seen some out of China too. I don't know what organizations, I haven't really looked into it, but it's really cool to see the rise of these huge models, and I'm excited to see what comes from them. We really don't know, and we can't know until we implement them and test them out. So that's really all I have to say for this video. If you like this type of content though, I do a lot of talking about research and all this sort of thing. So if it does interest you, do consider subscribing. It means a lot, and I'm gonna keep working my hardest to put out some good content. But that's all I have for now. So thank you so much for watching, and I hope to catch you next time.